Hello everyone, welcome back to the channel. If you just joined the live for the first time, make sure you subscribe and then like. Today we'll be covering something under electrical engineering, which we normally call applied electricity. This will be based on Ohm's law, basic circuits, series and parallel connections, and then the Kirchhoff's law. So now someone may ask, what is Ohm's law? So Ohm's law is just the basic of applied electricity. And when we talk about Ohm's law, is when we are relating the voltage, the current, and then the resistors, the components, the basic components that form a circuit. That's the voltages, the current, and then the resistors. So now Ohm's law can be expressed in a simple way, which is V equals IR. V equals IR. V equals IR. And then based on this V equals IR, we can make I the subject to find I and then R the subject to find our R. So now, let's say if you have a circuit with, let's say, a 12 volts across a 4 ohms resistor. So let's take our R to be a 4 ohms resistor. Then we ask you to calculate for the current. You know it's very simple because now you know V equals IR and now you have your V to be 12 volts and you have your R to be 4 ohms. So calculating for the current will be I equals V over R. So now a quick reminder and very short reminder. You should know that we always use the ammeter to measure the current, and then we use the voltmeter to measure the voltages. And taking note that when you are measuring the current, you are measuring the current of a circuit. When you are measuring the current of a circuit, we connect the ammeter in series with the circuit. And then when you are measuring the voltage, you connect it in parallel with the circuit. So now let's take this simple circuit. So sometimes there would be a switch in the circuit, and we know that switches, what the switch does is that it opens or closes the circuit. The switch open or close the circuit. Now, let's connect the components, some components in series. You see, we have resistors, and the resistors can be connected either in series or can be connected in parallel. So now, let's say we have two resistors in this circuit. How are we going to calculate for our voltage? Now, to calculate for our voltage, we know if we have two resistors in the circuit, we should check if the resistors are connected in series or in parallel. Now, let's focus on the series connection. After that, we move on to the parallel connection. Please, this is just the basics of applied electricity, and you will need this for the main event. So now, when do we say resistors are in series? So we say resistors are in series when the end of the resistors are connected to each other without any loop, without any junction or any other components in between them. So you could see with my resistor 2 and resistor 3, you could see there is no any junction. This is what we call a junction. There is no any junction in between, or there is no any component in between this. So now resistor 2 and resistor 3, they are in series. And you could see resistor 1 and 2 is also connected together. And then resistor 2 connected to resistor 3 connected to resistor 4. There is no any component in between the resistor 1 and 2, 2 and 3, 3 and 4. So now we can see all the resistors are in series. This is a live class, so if you have any question as we go, you can send it at the comment section and then you are going to get your answer. So now, when you look at the series connection, you could see there is the current flowing through all of the resistors remains the same. So the flow of current from the positive side of our voltage source to the negative. You know, current flows from a high potential to a lower potential. So the current will flow from the positive to the negative. So the current passes through the resistor 1, the same current will passes through resistor 2, the same current will passes through resistor 3, the same current passes through resistor 4. So now in series connection, the resistors have the same currents but different voltages. The voltage across R1, R2, R3, R4 may differ, and but the current flowing through R1, R2, R3, and R4 remains the same. So now let's say we have our voltage source here to be 10 volts. Let's say it's 10 volts, and then we have our R1 to be 2, this one to be 3, this one to be 2, this one to be also 3. So now to calculate for our current, we need to find our total resistance. So now we know V equals IR, right? So now to calculate for our current, we need to find the total resistance. And we know the total resistance, all these resistors are in series. So we add them. So now our total resistance will be 3 plus 2 plus 2 plus 3, which will be 10 ohms. Now we have our total resistance. So how do we get our current? Grouping like terms, we know that I equals V over R. V over R. We have our voltage to be 10 our resistor to be 10. So now our current becomes 1, our current becomes 1 ampere or 1 amps. Becomes 1 amps. Oh, sorry guys. Um, I didn't display the screen to you. Sorry guys. So this was what I was talking about. We have our resistors. We have our resistors to be in parallel. You see the resistors are connected to each other without any branches or any components in between those resistors. So now this makes these resistors to be connected in parallel. Okay, so now let's take it all again. Let's take it all again. When we say resistors are in series, the ends of the resistors are connected together without any component in between them or any junction. When we talk about a junction, let's say there is another wire here and there is maybe a component over there that forms a junction. If there is no junction and then the ends are connected to each other, then they are in series. So now, how do we calculate for resistors in series? To calculate for resistors in series, we sum up the resistance of the resistors. So now we have our R1 to be our R1 to be 2 ohms, R2 to be 3 ohms, our R3 to be 2 ohms, and then our R4 to be 3 ohms. To calculate for the total resistance, which is RT, we sum up the resistance, which is 2 plus 3 plus 3 plus 2. So now this gives us a total of 10 ohms resistor. So we have our resistor to be 10 ohms. Now let's move on. We are calculating for our current. We have our voltage to be 10 volts and we have our current also to be 10 ohms. Now, how do we calculate for our current? We know V equals IR. V equals IR, right? So we have V to be 10, I to be unknown. We don't know our I, but we know RT to be 10. Now we group like terms or divide each by 10. Then we have our I to be 1 amp. So this is basically for resistors in series. Resistors in series. Let's move on to resistors in parallel. So when do we say resistors are in parallel? When do we say resistors are in parallel? So parallel connection of resistors. We have two resistors over here, which is our resistor 1 and resistor 2. To know that resistors are in parallel or resistors are connected in parallel, you could see that across this loop, across this loop, there is no any other component across a loop, but only two resistors. Then you can say the resistors are in parallel. Then you can say these resistors are in parallel. Looking at this across this loop, you could get only two resistors. There is no any other component, only two. If the resistors are three, it doesn't make the resistors in parallel. There should be only two across a loop. Or you can say both ends of the resistors should be connected together. So we have here to be our node A and this here to be our node B. You could see that the end of this R1 is connected to R2 and the other end is also connected to R2. That's when we say resistors are in parallel. Someone may ask, how can we calculate for the total resistance if the resistors are in parallel? So if the resistors are in parallel, to calculate for the total resistance is 1 over the total resistance over the total resistance equals 1 over R1 plus 1 over R2. Now, you make RT your subject and then calculate for the total resistance, which will be RT equals R1 multiplying R2 over R1 plus R2. Let's work on some figures. Imagine we have R1. We have our R1 to be 4 ohms. Our R1 to be 4 ohms and our R2 to be 6 ohms. Now we have to find or calculate the total resistance. Now 1 over RT will be equal to 1 over R1 plus 1 over R2. you have RT to be equal to 4 times 6 all over 4 plus 6, which gives us 24 over 10, which is equal to 2.4 ohms. So take notice of something very important over here. You see, the total resistance, always the total resistance for resistors in parallel, they are always less than the smallest individual resistor. Looking at this, we have our okay guys, so our network is back. Let's continue. We move on to what we call the KCL and then the KVL. The KVL and KCL. The KCL states that the sum of the currents entering a node equals the sum of currents leaving the node. Now, KVL states that the algebraic sum of voltage rise and drops around a closed loop should equal to 0. So if you take this loop, the algebraic sum should be of the potential differences should be equal to 0. Looking at KCL, we have this. Let's take this to be current, our current, which was derived from this voltage source, which is IT. So we have our IT, and then looking at this node, we have IT to be entering this node, I1 to be leaving this node, and let's make this IA. We have IA to be also leaving. KCL states that I equals IA plus our I1. Now we move on to the next node. Having this node, we know IA will be equal to I2 plus I3. Should be 0. Now having this E to be our voltage source, E, the sum, E plus our IV, our V1, sorry, our V1 should give us 0. Someone may ask why or how. So in this case, we have our V to be negative. So we have E minus V1, which will give you your 0. We are just considering only this loop. Let's say we don't have this loop connected to our circuit, okay? Please don't be confused. I just want to use this to show you something. Now, KVL states that the algebraic sum of all the potential drops or across each of these components should equals the potential difference across each of these components should be equal to the voltage source. So now we have our E to be equal to V1 plus V2 plus V3. Plus our V3. So this circuit, looking at this circuit, we have our voltage source to be 45, and then we have R1, R2, and R3. Now 45 should be equal to the summation of the potential drops across each of these resistors. So let's take our current to be I. We know V equals IR. We know V to be equal to IR. So instead of using V1, V2, V3, we can use our I1 multiplying or our I multiplying our R1. I multiplying R1 plus I multiplying R2 plus I multiplying R3. So someone may ask, what if you sum up the resistors and they make it one? Yes, you can do that because the resistors are in series. So you can just sum up the resistors, which is 5, 10, 7.5. You sum them up together, then you get one resistor. So your circuit may look like this. F for the drawing, okay? And this will be your RT. This will be your voltage source, and then your current flows over here. Now let's move on to the current divider. We have what we call the current divider rule. So as we said, when resistors are connected in parallel, different current flows through them. So to calculate for the resistor, or sorry, the current flowing through each of these resistors, we have what we call the current divider rule. So before we continue with the current divider rule, let's take live questions for several minutes. You can type them in the chat. I'll pick them in order and then answer them. We have talked about the Ohm's law, which is V equals to IR, resistors in series and resistors in parallel. We know that resistors in series, they have the same current, but then different voltages. And then we know that resistors in parallel have this same voltage but different currents. Now we have the KCL, the current in equals to the current out at any node. We have the KVL, voltage up around any closed loop sums to zero, or the voltages of the components, or the voltages of, or the potential drop up of all the components is equal to the voltage of the source. So we are taking live questions. If you have any question, let's know in the comment section. So let's try our hands on some question. Some question. Okay. So I'm sharing the question to the screen. Try to solve the question and we will solve it together within some few minutes. We are back. So a main switchboard MSB at 230 volt supplies a sub-distribution board SBD via a 60 meters run of 16 millimeter square copper cable. So the resistance of the copper cable is 0.001 per conductor. So now the SBD feeds a 3800 watts resistive load through a further 20 meters of 2.5 millimeter cable. Calculate the load current. Calculate the load current. So we have now we have our P. That's the power to be 3800. And we also have our voltage. Our voltage to be our voltage to be 230. So now we have to calculate for the current. The current. So we know current per our formula. We have V equals IR. And now we looking at this formula, we don't have resistor. The resistance of our total or the total resistance over here. We just have our V and then we have to find our I. But we have power over here and we know P equals IV. P equals IV. So now to calculate for your I, you have your V and then your P. Your I becomes your P. Your I becomes your P over V. So now which is 3,000, sorry, 3,800 over our 230, which gives us 16.522 amps. So now So now, under full load operation, which is 230, the circuit will draw a current of 16.522 ampere. The second question, we have we have our I to be P over V. Looking at the formula V equals IR, we don't have the total resistance of the distribution. So now we use P equals IV. That's the formula for calculating or finding the power. To calculate for or to find our current. So grouping like terms, we get I to be equal to P over V. We have our P to be 3,800 over 230, which is equal to 16.22. The second question states that calculate the voltage drop across each cable selection. So we just solve the B and then you do the rest. We will continue maybe tomorrow. So we have a length of 60 m, that's 60 meters. That's the length of our wire. And then we have a resistance of 0.0027, which is ohms per meter. Now, to get our total resistance, we multiply the resistance of the cable to the length. So we multiply 60 times 0. We multiply this 60 60 times 0.0027, which gives us 0.162. Now to calculate for the voltage, which is V times V equals IR, we have our total resistance, sorry, our total current, which we calculated to be 16.5, 16.522 times 0.162, which gives us 2.677. Please continue with the rest of the questions. Continue. If you didn't take a screenshot, displaying the questions again, make sure you take a screenshot and then try your hands on them. So I think we'll be ending this session here. We'll meet tomorrow. Make sure you do your best to join tomorrow's class. Wish you all the best in your upcoming exams. Thank you. If you know you have not subscribed to the channel, make sure you do so. Thank you.